This is a lecture with real math behind it, and more specifically, the math behind the public key. Public key cryptography is built upon something you guys have known since you were a kid, maybe. Reading a clock. And by the end of this lecture, this operation that protects half the internet is going to feel much more familiar to you guys. So, let's begin. So, here's a core idea. If you look at a normal 12-hour clock, if it's 10 o'clock and you add 5 hours, what time is it? You didn't say 15 o'clock, you said 0 o'clock. You automatically wrapped around. You went up to 12, and then you kept on counting from where you started. You went from 12 to 1, then to 2 to 3. And wrapping around is the entire concept. In math, it's called modular arithmetic. The clock did it with a modulus of 12. 10 plus 5 on a clock equals 3. You've been doing modular arithmetic your entire life without knowing what it actually is. So let me give a proper definition. Now that you've already felt it, modular arithmetic asks, after you divide, what's the remainder? When we say 10 plus 5 modular 12 equals 3, we means 10 plus 5 is 15, and then 15 divided by 12 leaves the remainder of 3. The modulus, the 12, is the size of the world we're counting in. Everything wraps around once. It hits the top and starts over from 0. So for example, the clock, it's 12, wraps around to 1. A 12-hour clock is modulo 12. A 24-hour clock is modulo 24. Days of the week are modulo 7. Same idea, it's just a different size circle. Let's do a few quick ones to internalize the concept. Modulo 7. Imagine a clock with only 7 numbers on it. 0 to 6. So 0 through 6. What's 4 plus 5 mod 7? Well, 4 plus 5 is 9. 9 wraps around 7 once, leaving 2. Okay, so the answer is 2. What's 10 modulo 7? Well, 10 wraps around 7 once. Remainder is 3. What about 14 and 7? 14 makes exactly 2 laps, so the remainder is 0. So you land right back at the start. And that's all it really is. You count up, and wherever you pass a modular, you wrap back to 0. It's just laps around a small circle. It's fairly simple. Now, why is this used in cryptography so much? Well, there's 2 reasons. First, it keeps the number inside it fixed with finite space. No matter how big the input is, the result will always be somewhere on that small circle. Second, and this is mostly more importantly, it scrambles things in a way that's easy to do forward but very hard to undo. When a number wraps around a circle many times, knowing where you landed tells you almost nothing about how many laps you took to get there. And that easy forward, hard backwards is what we talked about, I believe, in the previous lectures. And it's a one-way property that we've talked about that cryptography is built upon. So to understand real cryptography, we need to add one more operation: exponents. Modular exponentiation just means to raise a number to the power and then take the modulus. It's still the same clock math, but just one more step. So what is 5 to the power of 3 modulo 7? Well, 5 cubed is 125, and now 125 around the 7 circle is, well, let's do the math. 125 divided by 7 is 17 with a remainder of 6. So we take 17 laps, and then we go 7. We're at 7. So 5 to the power of 3 modulo 7 is 6. It's easy enough when the numbers are small and you're going forward. But now, when you flip it around, that's where you'll see the security appear. Suppose I told you the answer was 6, and the modulus was 7, and the base was 5. Could you tell me what power I raised it to? Well, you have to guess. You'd try 5 to the power of 1, which is 5, and then you try 5 to the power of 2, and you try 5 to the power of 3, until you land on 6. With tiny numbers, you can brute force it. But if you make the modulus hundreds of digits long, finding that hidden exponent becomes effectively impossible, even though computing it forward was instant. This exact operation, modular exponentiation, that's easy forward but almost impossible to reverse, is what RSA and Diffie Hellman were built upon. It's a trapdoor. Anyone can compute in the forward direction with public information, but only someone with a secret can go backwards. Everything we said about public keys and private keys in last lecture has this type of clock math engineering underneath it. The public key lets you go forward, while the private key is a shortcut that basically no one else has. Now let me show you one of the most potent examples of this, Diffie Hellman, because it solves the key sharing problem we talked about, and it does it quite in the open. Picture two people who wanted to share a secret, but everyone can hear them talk. Think of it like, mixing paint. They agree on a common base color in public, and each secret mixes in their own private color. They swap the mixed results out in the open, then each adds their own private color again. Because mixing combines the same way regardless of order, they both end up with the identical final color, a shared secret, while anyone listening only saw the public mixes and can't unmix them. Under the hood, those colors are modular exponentiation. They built a shared secret over a channel everyone could hear. Now let me connect this to a failure you actually test for, nonce for use. Remember, nonce is a number that we're only allowed to use once. The reason why once matters is mathematical. Many of these schemes are safe only because each operation mixes in a fresh, unique value. Use the same nonce twice, and you hand the attacker two equations with the same hidden ingredient. And now, the math that's protecting it can be easily solved, and the secrets leak out. Not because the algorithm is weak, but because you're using the value broke the assumption that the math relied upon. This is why never use a nonce is very important. This also gives you a cleaner way to understand key sizes. The modulus defines the size of a circle, the space of all possible values. A bigger modulus means a vastly bigger space for a secret to hide in, and brute force means walking that entire space. Let's say a key must be a certain number of bits. What we're really saying is that the modular space has to be enormous enough that no attacker can search in it in any reasonable amount of time. A small modulus is like a small haystack with a findable needle, but a huge modular is a huge haystack that is almost impossible to solve. The size requirement is just make the circle too big to search. Here's the thing. Here's where it lands for you guys. You don't need to know the math by hand, really ever. But you should understand why the two rules are absolute. 1. Key sizes have minimum because they define how big that hiding space is. If it's too small, then it's searchable. 2. Nonce and IVs should never repeat because the security is mathematically built on each one being unique. When you see a config that has an undersized key or code that uses a nonce, you now know exactly why it's dangerous. Let's recap, and let's notice how far we've come. Modular arithmetic is clock math. Remember, you count around the circle, you wrap around the modulus, and you keep the remainder. Add exponents, you get an operation that's easy to go forward, but almost impossible to go backwards. It's a one-way trapdoor, and that's what makes public key cryptography possible. Nonce for use breaks the math directly, and key size is just the size of the circle where the secret hides in. That's the whole engine, and it's kind of like a clock. Next lecture, we'll answer the question this one opened up. Where do the giant numbers come from, and what makes them so hard to break? Spoiler, it's prime numbers, and we'll see exactly how the size of numbers turns into actual years of computing time to crack it. I'll see you guys in the next lecture. Bye.